The shorthand configuration, we'll practice that a little bit. Make sure it's crystal clear what Wednesday's quiz will involve: the history, shorthand configuration, and basic anatomy of the periodic table. And I'll go over that with us. And then we're going to start down the road of ion formation. Great thinking today. Absolutely fantastic thinking. All right. How did James Mendeleev, the father of the periodic table, accomplish what he did? How did he order the elements? If it's okay, can I correct that? No, the number of electrons have, nothing to do. Now, we could say placement somewhat reflects electron configuration, but the number of electrons, no. Yes. So Mendeleev, he was all about the atomic mass order, but other scientists, chemists had organized them in increasing mass. His genius, if you will, was leaving spaces for yet to be discovered elements. But Jeremy, we credit Mendeleev with the periodic law. Now it's been updated slightly, but Mendeleev's periodic law says what? Fantastic. And if we want to, what kind of properties? Well, they're chemical or physical. So chemical and physical. So they look similarly and they behave chemically very, very similar. Wonderful. But today, Jake W., we don't organize, we say the elements by atomic mass. We order them by, which we can also call, and we want to get away from, James, saying atomic number is the number of protons or number of electrons. Not always, but the atomic number is always the number of protons. Always. Dobenreiner, he grouped in threes. So we want to just know, like, in general, what the guys did. Newland's had the law of octaves. He put them in eighths, and it's when he stacked them on top of each other that the columns had similar properties. That was a really good step forward. All right. So what we were doing Thursday was mapping out the periodic table that's on the second page of your packet. And we were placing in the element block the very end of the electron configuration. Okay, so Allie, would you do us the honor of please choosing any element here in this third period in this section? I'm sorry? No, in this. Great. So thank you so much for saying in the P section, because we said we group the elements. The way it's ordered is by atomic number, but where it's placed is based upon electron configuration. That was beautiful that you said, well, chlorine, it's in the P block. So we know its electron configuration will end in P, but what P? As far as electron, we just count over 1, 2, 3, 4, 5. So the exponent will be 5. And the energy level that P is in is 3. I think I took a step too far. We need to backtrack. Let's go here. Aluminum. So aluminum has 13 electrons, 13. So if we're following the off-ball chart, 13, 2 go here, another 2, that's 4. Then we have 6, that's 10. We have 2, and then 1 in the 3p. So what we would write here, 3p, only 1 there. Next is silicon. Well, it's going to have 2 electrons in that 3p, and so on and so on. Do you remember we were doing this? Okay. How about vanadium? Vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Remember, we were seeing the trend that all group 1 have 1 electron in the s sublevel. Well, then the second group have 2 electrons in the s sublevel. And Jake G, it makes total sense then that we call this the s block with 2 columns, because the s sublevel can hold how many total electrons? Yeah. So we put 1 here and then 1 there. Okay. So here would be 3s2, 4s2, 5s2, and so on and so on. All right. Vanadium is here. After 4s, we go to 3d. 3d. So can we see the number that signifies the energy level for the S and the P sublevel is the same as the period number? The period number represents the energy level for the S and the P sublevel. But the D is 1 minus the period number. This is the 4th period, but when we get to the D block, it's 1 less. So the 4th period is 3D. The 5th period is 4D. The 6th is 5D. The 7th is 6D. Huh? And does it make sense, Preston, that this would be 3D1, 3D2, 3D3? Yeah? Okay. So, concerns before I show you this shorthand map? Yes.
In the bottom right, you drop off to the F series. What do you write in those ones?
We're not there yet. Okay. So can we practice a little bit before there, please? And then we'll get there. Thank you for asking. If you don't mind, if you can give us 5 minutes, then we'll get to that. Okay. You do not have, please just watch what I'm doing. Please watch what I'm doing. Okay. If we would have the electron configuration of magnesium, it is 1s2, 2s2, 2p6, 3s2. Okay. Eddie, how many valence electrons does magnesium have? Where are they? You got it. And what name do I give? What nickname to all the electrons that are not valence? Inner core. Inner core. All the electrons in an element are important. But for reactivity, it's valence that are the most important. Magnesium is in the 3rd period. We know that this final column all the way on the right are called the noble gases. Magnesium is in the third period. If I go one period above to neon, in the second period, that's the noble gas. And neon has the configuration 1s2, 2s2, 2p6. A shorthand way that we can write electron configuration. You take your element and you begin with the noble gas that's in the period above it. So magnesium is in period 3. We go up and go over to the noble gas, the 18th column, and we get neon. So if we write neon in brackets, we are saying all the electrons that are in an atom up to neon. So all of its 10 electrons. Then we begin in the third period. So if I write neon in brackets, all of those from hydrogen over to neon. Then I begin in the third period and I work my way over to magnesium. Now, magnesium here, second position of the S block. Which S? Third period down. Done. Can we still answer number of valence electrons? Yes. Where are the valence electrons? How many inner core? How many paired? How many lone? And still answer all the questions that we know how to answer. So it's not that much of a chore to write magnesium's electron configuration. How about tin? So tin, I go to the noble gas before it, krypton. So tin, 1, 2, 3, 4, fifth period. So I want to go to the fourth period noble gas. So that means all the electrons up to krypton 36. But then I have to start building until I get myself to 10. All right, so where do we go first? The S block. Okay. Which S? The 5S, right? Yes. Okay, so 10, the second. 1, 2, 3, 4, 5. Okay. So I have to work my way through 5S. Do I need both of them? Yeah. That'll get me here. Then I enter the D block, and what we have to remember is the D is 1 minus the period number. And I need all of these to work my way over to 10. Yeah? So 4D, 10. Okay, so 5S2, 4D, 10. Then I enter the P block, which P, same as the period number. And 10 is 2 positions over, so 5P2. You can do the same for orbital notation. We would do krypton and then 5S, 4D, and then 5P. Questions on those two? Okay. So now to your question, Jacob. On the periodic table, right? After barium is lanthanum. After radium is actinium. Okay, if we look on the periodic table, okay, this is 6 and 7. So this is 6S and 7S. Well, where do we go after 6s? Done. 4f. So we have to remember this. After 6s, then different color. We go all of these, then back up to the 5D. After the 7s, then we fill the 5f. Yes, sir. Oh, I apologize greatly. Thank you. Thank you so much. And then go up to the 60. So, let's see. Patty, could you pick something in the D block, 72 over to 79? Sounds good. So if we were going to do the electron configuration of tungsten, all right, so tungsten, yes, is 4 over. Yeah. Okay, noble gas before, xenon. Then I start working my way first through 6s. I need both of them. But then, make sure we get 4f. Then we come back up to the 5D, and then it's 4 over. If we don't include the 4f14, we don't have the configuration of tungsten. We would only have 6 electrons beyond xenon, which would be 60, which is this element. Okay, so if you add up, like for 10, okay, krypton has 36 plus 12, 14. And so that gives us our 50 total, which is what we need for 10. So we could double check really quickly by adding up what you added to the noble gas to the electrons the noble gas has. Now, students will often, if I ask, let's say for argon, but that is not following the procedure. No, you go to the noble gas in the period above, the period above. So it would be neon. 3s2, 3p6. Sorry. No. Okay. Questions for me? Okay, in our packet. Yes. Okay, can I tell you that lanthanum is a member of the D block. So lanthanum is a D. Actinum is a D. Okay, so there should just be, let's see, 2, 4, 6, 8, 10, 12, 14. Lanthanum and actinum really, see, I love that periodic table in the back. That one, do you see, it has lanthanum and actinum. They are D block elements. That's where we measure the D to B. So for lanthanum, it would be 6s2, 5d1. Done. So lanthanum actually is a D block element. I'm sorry? You, Izzy. Did Addie, did Izzy address? Okay, let me know if not. Any other concerns? Okay, so in our packet, can I ask you please to turn to page 5, please? Nathan, would you do us the honors? So we already did tungsten. So would you do the honors of choosing another one? Absolutely. Oh, I'm so sorry. Of the list. I'm sorry. Okay, let's do potassium. And how about ruthenium? And we will do, how about also selenium? Okay, can we just do the shorthand notation for those 3, please? Just those 3. Thank you, Nathan, for choosing that. And please ask me anything that you need. How about polonium? Discovered by Madame Curie. She named it after her native land of Poland. Any concerns? And it would be so good for us to just check that we did. So polonium, total of 84 electrons. So 16, 26, and 30 that we've added. Oh, there we go. So it should reveal itself if you've forgotten the F block. That's really easy to do. So just give a moment to check. Yes. Okay, so by putting the noble gas that is in a period above it in brackets, that means all the electron configuration that xenon has. So that means 1s2, 2s2, 2p6, 3s2, da 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 da. So that's the method that we've developed. That if you put them in brackets, that means all the configuration. So that stands for the big long written out. So you look at where your element is that you're trying to get to. Okay. And like on that, the periodic table that's in the beginning of your, the reason I had us put that last position of the electron configuration was for us to see that the actual structure of the table, now the order, why hydrogen is here, helium, beryllium, why they're in the order they are, or I'm sorry, lithium, the beryllium, is increased atomic number. But why we have these columns sticking up, then we have this chunk up, the structure is based on electron configuration. So when we were placing these, did we see that these elements and their configuration in the S sublevel? So we said all of these belong to what we call the S block, and then P, and then D, and then F. Okay. So if you're working your way to here, okay, the noble gas before it, xenon, put that in brackets. Okay, then I'm going to start in the 6th period and I need to work my way all the way over to that. So first, I go through the S block. I need both. It's like I'm adding. So I need both positions. So it'll be 6s2. But then, ding, 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 I need to go to the F because that's what we do. And that has 14. And then I go back to the D. Do you see? So we're like making our way over to that element, adding, knowing what block you're going through. Yep. Because we don't place electrons there. We don't start placing the F until after. Yeah, until we're in that 6th period. Yeah. Did that address what you need? Okay. Any other concerns? Yes. We get this order from the math that Schrodinger and Planck and all those guys, Heisenberg, figured out. And we place electrons from the lowest energy to the highest. And so it just so happens that after 6s, then we fill the first position of F, which is in the 4th energy level. So as we go from hydrogen to our, through our, all of our elements, yes, we increase by proton. But we're also placing electrons in a certain order. Okay, so After 6s, we fill 4f. That's what the math tells us. And we can measure it, by the way. Okay. Now, if we want to like match, and that's why I had given us another graphic. Opposite of the page that, if you just want to look at what I'm showing, opposite of the page that we just did the shorthand configuration on, this actually shows like the order really of our elements. Really, we just pulled these out of the periodic table to have it fit better on. Yeah. So here or here, you can see 6s, then 4f. So that's the order that we fill electrons from lowest to highest energy. And it's what the math tells us. So because we're ordering with increased proton, it's also going to mirror where we're putting electrons in our ground state. And so as we travel across a period, we're actually like satisfying the off-ball chart. I don't know if that answers what you need. Absolutely, I know. So the period number matches the S and the P, but D will be one less than. In the fourth period, it's 3D, and so on. Yeah, so, okay. So I hope as we're practicing that we can like see, oh, that's the S block. Oh, that's the P. And then we know the number that matches the energy level is the same as the period number. So if you put some thought into it, and we're going to keep practicing it, we'll get it. All right. Could I ask us, please, to turn to page 7? Okay, just a little bit of anatomy. Just a little bit of anatomy. And by anatomy, I mean like parts. Yeah, like where is what? Okay. A group and a family. That is the official name for columns on the periodic table. Oh my gosh. Who's our speller? Go ahead. I know for some reason, do you ever like write a word and then you're, gosh, I'm an old person. How can I not? But I was questioning it. I didn't want to be wrong for you guys. Thank you. Vertical columns. Vertical columns we can call group or families. A series is a particular grouping of elements. A series is a particular grouping. And we only have 2 series on the periodic table. They are the F block. And you'll always have a periodic table. We don't have to memorize this. The first row of F, we call the lanthanides because cerium, the first F block element, follows lanthanum. So these are the lanthanides and then actinides. And lanthanide series, actinide series. So a series is a particular segment of a horizontal row. That's what we call a horizontal row is a period. And this is a specific portion of a period. All right. On this, can we please add the staircase? All we have to ever remember is it begins under boron. Yeah. Ryan, where do we find metals on the periodic table? Just here? You're exactly correct. So all of these, except for hydrogen, not hydrogen. So all of these. Now, what about our F block? Are they metals? Go ahead, Jacob. Okay, where do they fall? The F block falls after the S block. Yeah. So these, remember, are up here. These are also metals. Okay, but not hydrogen, not hydrogen. And then, of course, to the right, non-metals. Now, we know we have this small category that we call metalloids, but an element is either going to react like a metal or a non-metal. We only consider something to be a metalloid if we're looking at electrical conductivity. That is it. That is it. That is it. I know we talked about that before. So what is the main characteristic that makes a metalloid a metalloid? It is a semiconductor. It's just okay, which is perfect for our technology. Okay, you know this already. What are properties of metals? I'm asking for 4 of them. Go ahead, we have it. Go. Yes. Of what? And in what form? Yeah. So, metals are excellent conductors. And do you know there's some things that can conduct electricity, but not heat, and some that conduct heat, but not electricity? They do both excellently. Can we get another? Do you remember what that means? Wonderful, wonderful. They are lustrous, shiny. They are, except for one, solid at room temperature and pressure. What color? Metals, metals, metals. I know that's the 5th. Gray, or we could say silver, but I like gray. Perfect. And we could do EY or AY. I know. Either. So, non-metals, most important thing, they are non-conductors. They do not conduct heat or electricity. 0. They are brittle. So when force is exerted, they break. They don't mold. They are normally gases and liquids at room temperature and pressure. And they are colored, even though gray is a color, they're not gray. They're colors other than gray, we should say. All right. Could I ask us, amazing students, for tomorrow, in the back of our packet, we have those section reviews. So could I ask us, it is page 22, easy peasy, not more than 5 minutes. So could I ask us to answer 2 through 5, and then 9 through 14. 2 through 5, 9 through 14. Page 22, 2 through 5, 9 through 14. Remember our quiz, our first quiz on electron configuration, shorthand, history, basic anatomy. So everything up to today. Fair game for Wednesday. Oh, we didn't have time for a lab. We'll do that tomorrow. Promise.